Hello, welcome to Management Science Studio. I'm Vahid Lotfi and I'm an Emeritus Professor of Management Science. In this video, I will demonstrate how to solve a project management problem using the critical path method or the CPM. So let's get started. Here's an example problem with 7 activities A, B, C, D, E, F, and G. And we can see the precedence relationship. We have the start activity that doesn't have any predecessor and no duration. Activity A follows the start activity, or its predecessor is start. Similarly, B, the predecessor is start. Activity A duration is 5 days. Activity B is 3 days. Activity C follows A and it's 6 days. D follows B and 4 days. E follows C with 3 days. F follows both C and D with 5 days. G follows E and F with 6 days. And finally, the finish activity follows G and 0 duration. I placed this arrow here for making it easier to draw the precedence relationship diagram. The first step in the solution process is to draw the network diagram, and we'll go ahead and select this cell as the node for the start activity, and then followed by A and B, which follow the start. I'll place A here and I'll place B here. And then draw the arrows. So I'm just copying and pasting. So the arrow signifies the precedence relationship. Okay, now I'm ready to draw activity C. So I'll place activity C in this cell here. Draw the arrow. And then label it. And notice that activity C follows A right there. We go to activity D, which follows B. So we'll place D here. And we'll do the arrow. Okay, now I'm ready to go to activity E, which is following activity C, or we can place activity E here. Again, with the arrow, connecting the two activities, and we go to activity F, which follows both C and D. I'll place F here. Now I need two arrows, one going from C to F, and a second one going from D to F. So we can see that F follows C and D, or the predecessors of F are C and D. And finally, activity G, which follows E and F, so we'll place G here. And we need arrows to connect them. One more. And the last activity is finish, which follows G, so we'll place finish here. We are now ready to solve the project management problem using the critical path method. I have prepared this worksheet to go through the solution process. But first, some definitions. The parameters are needed to solve the critical path method. First, earliest finish time, which is equal to the earliest start time plus the activity time. Then earliest start time, which is maximum of earliest finish time of all of the predecessor activities. Next, latest start time, or LS, which is latest finish time minus activity time. Then latest finish time, or LF, which is the minimum of the latest start time of all of the following activities. The next one is slack time, which is either latest start time minus earliest start time or latest finish time minus earliest finish time. And finally, the critical path. The critical path consists of the set of activities that have zero slack time. In order to apply the critical path method, we have to make two passes through the network, one forward pass and one backward pass. In the forward pass, we will be calculating earliest start time, earliest finish time, all the way to the end. In the backward pass, we will be calculating latest finish time and latest start time. So let's go ahead and get started. With the first activity, obviously on the start activity, the earliest start is 0 and the earliest finish is 0 because there is no activity time. So the earliest start time of activity A is the maximum earliest finish time of the predecessor, which is 0, so this is going to be 0, and the earliest finish time is going to be earliest start plus the activity time, which is going to be 5. Similarly, for activity B, earliest start is 0 and the earliest finish is going to be 3 because the activity time is 3. We move to activity C, and in activity C, the earliest start time is going to be the maximum of the earliest finish time of the predecessor. In this case, it's going to be 5. And the earliest finish time is the sum of the earliest start and the activity time, which will be 11. For activity D, the earliest start is going to be the earliest finish of B, which is 3, and the earliest finish time is earliest start plus activity time, which will be 7. Next is activity E. In activity E, the earliest start is the earliest finish time of predecessor, which is 11 for activity C, and the earliest finish time is going to be 11 plus 3, which is 14. For activity F, however, we have to worry about two earliest finish times, one up here and one down here. We have to take the larger, and that's going to be 11. And the earliest finish time, as usual, is the earliest start plus the activity time, which is going to be 16. Now we move to activity G. Again, here we have to worry about two earliest finish times for E and F, and take the larger one, which is 16. And the earliest finish is going to be 16 plus 6, or 22. And we go to the finish event. The earliest start time is going to be the earliest finish time of G, which is 22. Finish activity doesn't have any activity time, so its earliest finish is going to be 22. We are now ready to make a backward pass and calculate the latest start and latest finish time. So starting with activity G, the latest finish time is going to be the minimum of the latest start of the follower, so that's going to be 22. And the latest start is the latest finish minus the activity time, which is going to be 16. We go to activity E. The latest finish time for this activity is going to be the minimum of the latest start of the follower activities, which is going to be 16. The latest start time is going to be latest finish minus the duration, which is going to be 13. Now we go to activity F. The latest finish time again is going to be 16, which is the latest start of the follower activity, and its latest start is latest finish minus activity time, which is going to be 11. We go to activity C. The latest finish time is going to be the minimum of the latest start of the follower activities. The latest start of the follower activities are for E, which is 13, and for F, which is 11, and the minimum is 11. and its latest start is latest finish minus activity time, which is going to be 11 minus 6, which is 5. We go to activity D. The latest finish time is going to be the minimum of the latest start of the follower activity, which is 11, and its latest start is latest finish minus activity time, which is 11 minus 4, and that's going to be 7. Now we go to activity A. Its latest finish is going to be the latest start of activity C, which is 5, and its latest start is latest finish minus activity time, which is going to be 0. And we go to activity B. Its latest finish is the latest start of the follower activity, which is 7, and its latest start is 7 minus 3, which is 4. We have calculated the earliest start time and earliest finish times. We have calculated latest finish times and latest start times. Now we are ready to calculate the slack times, which by definition is either latest start minus earliest start or latest finish minus earliest finish. So we go to activity A, and its latest start time is 0. Its earliest start time is 0, so the slack time for A is 0. We go to activity B. The latest start time for activity B is 4. The earliest start time is 0, so the slack time is 4. We go to activity C. The latest start time is 5. The earliest start time is 5, so the slack is 0. We go to activity D. The latest start time is 7. The earliest start time is 3, so the slack is 4. We go to activity E. The latest start time is 13. The earliest start time is 11, so the slack is 2. We go to activity F. The latest start is 11. Earliest start is 11, so the slack is 0. We go to activity G. The latest start is 16. The earliest start is 16. The slack time is 0. We can now identify our critical path. By definition, activities that have 0 slack time constitute the critical path, and I'm going to mark them with red color. Starting with activity A, we can see that the slack is 0, so A is on critical path. We're just going to mark it with red. We go to activity B. The slack is 4, so B is not on the critical path. We go to activity C. C has a slack of 0, therefore C is on the critical path. We go to activity D. D has a positive slack, so it's not on a critical path. We go to activity E. It has a slack of 2, it's not on the critical path. We go to activity F. It has a 0 slack, so F is on the critical path. We go to activity G. G has a slack of 0, so G is on the critical path. And obviously the start and finish activities are on the critical path. So we can see our critical path is A, C, F, G. This is how the critical path method is applied to project management to identify a set of activities that are critical to the project, and if they are delayed, they will delay the entire project completion time. On the other hand, activities that have positive slack can actually be delayed up to a certain point without delaying the project completion. Let's take a look at, for example, at activity B. Its earliest start is day 0. Its latest start is day 4. It has a 4-day slack time. That means this activity can start as early as day 0, or it can be delayed up to 4 days and start at day 4 without delaying the project completion time. Similarly, activity E can start as early as day 11, but it can also be delayed by 2 days and start as late as day 13 without delaying the project completion time. And that is how we apply the critical path method to a project management problem to determine the set of critical activities in order to complete a project on time.